So, hello everyone again. This is lecture number 5 of motion in a plane. So, today we will be going on with the further discussions regarding the motion in a plane analogy in terms of your vectors. So in the previous class, we have done about position vector and velocity vector. Today, we will start with a new discussion about the acceleration vector and move on. Okay. So, today is lecture number 5 of motion in a plane. I am Samir Lawankar. Let's begin our discussion. Okay. So, course outline first of all, so that we are in sync with everything which is going on, which are whatever things which you are starting to understand. Okay, so right now we are on the seventh point, that is motion in a plane basically. Before this, we have started with the introduction in which we understood as in how we propagated our dimensions from one dimension to two dimension. So before this, we had a topic, we had a chapter called as motion in a straight line. Motion in a straight line, right? So that was based upon only use of a single dimension, correct? So either it can be x or it can be y or it can be z, correct? So there can be only usage of one dimension, that is x or y or z. Okay, so basically we would have used only positive or negative in that sense and could have solved the examples. So different attributes are being explained in that chapter, so you may go and look there. Kinematics was basically introduced in this chapter. So moving on, when we add a second dimension into it, so we understood that complete motion in a 2D plane, which was called as motion in a plane. So basically either we use xy or we can use yz or we can use zx, correct? So that was completely the introductory part of motion in a plane. Then we understood two different quantities. One is vector quantity, one is scalar quantity. So basically scalar had a scalar had a magnitude and the vector had a magnitude plus direction. Fine. Then simple properties about vectors and scalars were being understood. So scalars can be directly used as algebraic operations can be directly implemented in scalars, whereas this cannot be directly implemented in vectors, right? So that was the basic concept which you understood in this third, fourth, fifth, and sixth point regarding your vectors, correct? So in the third point, we understood one of the property, that is multiplication of vectors by real numbers. Then we understood about the graphical method of addition and subtraction of vectors. So basically it's just a plus b, correct? And if you need to subtract, so that is nothing but a plus of minus. Okay, so that is how we do the subtraction, correct? We understood that vector is basically a quantity which has a magnitude and a direction, and it follows two different rules, or basically called as your parallelogram law of addition or a triangular law of addition, which is another rule. Okay, so triangle law of addition. Okay, so what does the parallelogram law of addition says? The parallelogram law of addition basically says that, let us suppose that there is a vector a, there is a vector b. Let us say this is the vector number a, let us suppose this is the vector number b. Then the resultant will be this vector r, which is a diagonal of the supposedly parallelogram being formed here. Similarly, for triangle law of addition, let us suppose this is vector number a, and let us suppose this is your vector number b. Then the resultant will be from the tail of a to the head of b, which is this is the resultant, which is nothing but equal to a plus b. Okay, so that was the parallelogram law of addition and the triangular law of addition. Fine, moving on, then we understood the resolution of vectors, in which we understood basically that any vector a can be resolved into two different vectors that are in the same plane by multiplying it by a suitable factor, let's say lambda here and mu here, correct? So this is also a vector, this is also a vector, and this is also a vector, right? On the similar terms, to make the calculations easier, to make the vectors to be working in the xy plane, we said that the vector a can be said as the addition or summation of two different vectors, one in I form, one in j form, as we can write this as axik, and this will be ayjk. Okay, so these all things are being understood. Let us suppose if you need to draw this on a diagram, on a graph, so it will be x here, y here. So therefore, this will be your ax, this will be your I cap, this will be your direction of j cap, And if this is your if this is your A, and if you drop on perpendiculars from here, so this is the magnitude of your x component, and this is the magnitude of your y component. Okay, so that is how we understood the resolution of vectors. And finally, in the sixth point, that is vector addition, we understood the basic formula for vector addition, which came out to be r is equal to nothing but under root of a square plus b square plus 2ab cos theta. Correct? Then this was called as the cos theta is being used. This is called as your law of cosines. And similarly, there was a law of sines. Okay, so those all things are being understood in that chapter, in that discussion only. So you may go and look back to that. So now let us move to the concept of motion in a plane. Okay, so let's start discussing motion in a plane, and then we can move forward. Fine. So let's start the discussion directly. So these all things were being understood. Okay, just a quick revision again. So what were all the basic vectors which we understood in this chapter? The first started with the position vector. The second was your displacement vector. The third was your zero vector. And the fourth was your unit vector. Okay, just a brief description of everything. So what is basically position vector? Let us suppose we draw a graph with this the x-axis, this has the y-axis. If this is the position P here, then the vector drawn from the origin O, the reference point O, to that position is basically called as the unit vector. Okay, now let us suppose that the x and y coordinates at time t were this, and it moved from this place to this place. Let us suppose this is your p dash, so it will have the coordinates x dash and y dash. And the position vector from P to P dash, the vector from P to P dash will be nothing but called as your displacement vector. Okay. Then what is zero vector? Zero vector is basically a vector which has a zero magnitude and has a direction. It has a direction but cannot be specified. Okay. Similarly, what is unit vector? Unit vector has a magnitude of 1 and it is generally in the direction which are specified. So basically I cap, let us say the example of unit vector. So I cap, which is in the direction of x-axis, y cap, which is in the direction of y-axis, and j cap, which is in the ij, k cap is in the direction of z-axis. So I cap is in the direction of x-axis, j cap is in the direction of y-axis, and k cap is in the direction of z-axis. Okay. That being said, we understood the x position vector and the displacement in the last lecture only. So basically we calculated that r bar is nothing but equal to xi cap plus yj cap. And similarly for the displacement part, we understood that is equal to delta r, which is equal to delta xi cap plus delta yj cap, where delta x is nothing but x dash minus y x, and delta y is y dash minus y. Fine. That thing being said, let's move forward. We also understood in the previous discussion only regarding the velocity concept, in which you understood that what is velocity? Velocity is basically v bar, basically delta r by delta t, which is equal to vxi cap upon plus vyj cap. In the similar terms, you also understood the instantaneous velocity, which when calculated forward came out to be equal to dr by dt. And finally, we obtained that to be in the same form as vxi cap plus vyj cap. Okay. So that's how we can, this is how we can, if Vx and Vy are known to us, we can calculate the velocity as equal to under root of Vx square plus Vy square. And similarly, we can calculate the value of theta as tan theta is equal to Vy by Vx. Therefore, theta is nothing but equal to tan inverse Vy upon Vx. Fine. Okay. So that thing being said, let's start today's discussion from the acceleration of understanding acceleration as a vector in the motion in a plane. Motion in a plane, basically, let us take in the consideration here that motion is across the xy plane. Okay. So motion is along the xy plane. Let us try to understand this here. Okay. So the average acceleration a of an object. So this is a bar basically. This is your a bar basically. The average acceleration a of an object for time interval delta t moving in the xy plane is the change in the velocity divided by the time interval. Okay. Therefore, what we can say, that is a bar, which is equal to delta v upon delta t, which is equal to, in the place of delta v, what we can write, we just derived it in the previous section only. That is nothing but equal to Vx I cap plus Vy j cap. Now delta can be used for the both the properties here, so we can just multiply directly here and here, and hence we will get delta Vx upon delta t I cap plus delta Vy upon delta t j cap. Or we can write this as equal to A bar, which is nothing but equal to Ax I cap plus Ay j cap. Okay, fine. Next, let's move on. So the next line states that, so this is basically in this terms only. So as we know that what is Ax can be said as delta V in the x direction upon delta t, and similarly what is Ay is nothing but delta V in y direction upon delta t. Okay, fine. Next thing, the acceleration, that is the instantaneous acceleration, is the limiting value. So now what we are just doing, how to understand limiting value, we just write this as equal to limit delta t tending to 0. Okay, so limit of the acceleration, average acceleration. So what we will do, we will just write here A bar. Now we know this is nothing but equal to limit delta t tending to 0 del v upon del v. Okay, and that is the form which is written. Okay, so it's delta v upon delta t. Okay, as the time interval approaches 0, so that is why we wrote delta t tending to 0. Okay, now since we know that delta v is nothing but equal to delta vx I cap plus delta v j cap, so as in the similar terms we wrote delta x is nothing but equal to delta x I cap plus delta y j cap for the displacement part, right? So in the similar terms, or we can write this as, so as this was being written, that is delta r is nothing but equal to delta x I cap plus delta y j cap. In the similar terms, now what we are doing, we are just trying to find out that delta v is nothing but equal to delta vx I cap plus delta v j cap, delta vy j cap. Okay, so therefore just with the similar results we can write just limit can be across the same portions here, right? So therefore this will be nothing but equal to I cap into limit delta t tending to 0 delta vx by delta t, and similar delta vy by delta t. Okay, and that leads us to directly Ax I cap plus Ay j cap again. What is Ax here basically? It is dvx by dt, and what is Ay here basically? That is dvy by dt. Okay, so if we are talking about average acceleration, then also A is nothing but equal to Ax I cap plus Ay j cap. Okay, and even if you're talking about the instantaneous acceleration, then also A bar is nothing but equal to Ax I cap plus Ay j cap. The only difference is that in the first example, Ax and Ay takes the form as delta Vx by delta t and delta Vy by delta t, correct? But in the second form, it takes the notation that is dvx by dt, and similarly it takes the form dvy by dt. Okay, so it is nothing but the limit of this delta t tending to 0 and the limit of this delta t tending to 0. Okay, so that is the only difference between the normal average acceleration and the instantaneous acceleration. Fine. That being said, let's move forward. Now let us understand the same analogy which we understood for the case of your velocity. So let me just iterate. So as in the case of velocity, we can understand graphically the limiting process used in defining acceleration on a graph showing the path of the object motion. Okay, so let us understand what is being happening here. So this is shown in figure A to D. So just look at the figure A to D clearly. So P represents the position of the object at time t, and P1, P2, P3. So this is P1 basically, this is P2 basically, and this is P3 basically. After time delta t, delta t1, delta t2, delta t3 respectively, where delta t1 is nothing but equal to delta t1 is greater than delta t2 is greater than delta t3. Okay, so this is the similar case which we understood in the example of your the previous velocity concept also. So similar thing has been explained here. The velocity vectors at points P, this is P, P1, P2 and P3 are also shown in the figures A, B and C. Okay, so velocity vector is also shown here. Okay, moving on. So in each case of delta t, delta v is obtained using the triangle law of vector addition. Okay, so how we are obtaining delta v? We are just obtaining delta v as a thing but using triangle law of vector addition. Okay, so as this is the velocity v there, this is the velocity v dash there. Okay, so this delta v will be nothing but, as we know that delta v is nothing but equal to v dash minus v, correct? So this is nothing but a simple example of using a vector subtraction, correct? So vector subtraction when obtained, then this can be obtained as the value of delta v as the case goes on. Okay, so as you can see that this is your v here, this is your v bar here. So we are just putting this v bar onto this onto the tail of v, and hence obtaining the value of delta v, right? So therefore, by definition, the direction of the average acceleration is the same as that of delta v. So this is quite clear because we know that what is average acceleration? It is nothing but equal to delta v upon delta t. Therefore, the direction of delta v would be same as the direction of delta t. Sorry, delta a. Why? A bar. Why? Because delta t is a scalar and it is nothing but is multiplied or divided by a factor, and hence that does not change the value of the direction. It just changes the value of the magnitude of the vector. Okay. So we see that as delta t decreases, the direction of delta v changes. Okay, as you can see, the value of the direction of delta v is keep on changing. Okay, so it cannot be seen very clearly here, but if we go at a very magnified stage, then it is easy to be observed there. Okay, so the direction of delta v changes and consequently direction of acceleration also changes. Quite evident if the value of delta v, sorry, if the direction of delta v is changing, then the direction of delta a will also change, or a bar will also change. Not the delta a, sorry, it's a bar. So if the direction of delta v will change, if this will change, then the a bar will also change. Why? Because by definition, the direction of the average acceleration is the same as that of delta. Okay. So finally, in the limit delta t tending to 0, so when we are trying to decrease, as we keep on decreasing the value of delta t, the average acceleration becomes the instantaneous acceleration and has the direction as shown below. Okay, so we just keep on doing that, and finally what we found, that what is the value of direction a, that this is the direction a at the instantaneous location. So note that in one dimension, the velocity and the acceleration of an object are always along the same straight line, either in the same direction or in the opposite direction. Okay, so quite evident the velocity and acceleration will be same because acceleration is nothing but some factor is multiplied with velocity vector, correct? So direction will change. Direction will be same, the magnitude will only change. Only the direction will be same, the magnitude will change. However, for the motion in 2 or 3 dimension, the velocity and the acceleration may have any angle between 0 and 180 degree between them. Okay, so for 1 dimension, the direction is always same, but for 2 or 3 dimension, it may vary also. Okay, as you can see clearly here that this was the velocity direction and this was your acceleration direction. Okay, so delta v direction would be same as a, but velocity can have a different direction and then acceleration can have a different direction. Why? Because acceleration is rate of change of velocity. It is not equal to velocity, it is rate of change of velocity. That's why direction of a would be same as that of delta v, but it may or may not be equal to direction of v. Fine. So I think that was a simple basic rule which you need to understand. So that being said, let's move on. Okay, now let us look at the example, one of the example in which we will try to find out the value of d and t here, and hence let's understand this example. Okay, so the position of the particle is given to you in the question, that is r, which is equal to 3 t I cap plus 2 t square j cap plus 5 k cap. Okay, so I wrote this unit vectors as bold here, so you can understand those to be vectors only, and those are actually in the form of caps. Okay, so I may have omitted somewhere in the locations caps here, but you can understand that those are nothing but your unit vectors which are basically written or represented here. So in your exams, try to represent I, J and K like this only, and that would be beneficial. That is the actual representation of it. Okay, fine. So we have the vector given here, that is r is equal to, so as you can understand, this is a r. So what can be done from this? It is a position vector. This is a position vector. Okay. Let us look at let us understand this more about the situation here. So what is R here? R is nothing but 3t I cap 2t square j cap plus 5k cap. Okay, so let us say what is happening here, that is with the variation in time, the value of the position is changing. Let us see what happens when we put t is equal to 0. When we put t is equal to 0, what is the value of r? It is nothing but 0 I cap plus 0 j cap plus 5k cap. What does it mean? It basically means that if you draw a 3D space like this, let us suppose this is your x, this is your y, and this is your z. What is the present position of the value of, what is the present position vector aligned at? It is aligned at this location here. So this is basically the position vector, with this to be 5 units in the z direction. Okay, let us understand more. Let us say we need to find out the same thing at t is equal to 1. Okay, so what happens at t is equal to 1 second? So again, we'll calculate the position vector. It is nothing but equal to 3 I cap plus 2 j cap plus 5k cap. I am doing nothing. I am just putting the value of t in this position, in this point. Okay, so fine. So that thing being said, so what can we understood from this situation now? It is nothing but equal to 3 at this, 2 at this, and 5 at this. So therefore there would have been some place which is somewhere here where the position would have changed from, let's say, t is equal to 1 to t is equal to 0 to t is equal to 1. Now the path would vary because I cannot actually draw the graph as if I don't know the initial values between 0 to 0.1. So I need to find it out for 0.1, let's say 0.2, 0.3, 0.4, 0.5, 0.6 till 1, and then we can join them, and then we can understand what is the path actually of the part. Okay, so that was just being done to make you understand what is basically a position vector doing. Okay, fine. So where t is in seconds and have coefficients have the proper units, and coefficients have the proper units for r to be in meters. Okay, so first of all, the question says that we need to find out the v of t, and the second question says that we need to find out the a of t, and finally what we need to find out the magnitude and direction of v of t at t is equal to 1. Okay, so let us first of all right now look at first part only, and then we can move forward. Okay, so on the discussion which you have already done, we know that what is the value of v? V is nothing but equal to, for the instantaneous, okay, we are talking about instantaneous here, correct? It is nothing but equal to dr by dt. Okay, so what we will do basically, v is v bar, or v is nothing but is equal to vx I cap plus vy j cap plus vz k cap, correct? Where Vx is nothing but equal to d Rx by dt. Vy is nothing but equal to d Ry by dt. Vz is equal to d Rz by dt. Correct? What is Rx, Ry, Rz? These are nothing but the resolved components of the position vector which is given to you in the question. Okay. So evidently what we can say, that this is your Rx 3t, this is your Ry which is 2t square, and this is your Rz which is 5k. Please remember that this is the component which is to be used. Okay, fine. So let me just put everything here. So it is nothing but d by dt of 3t. Similarly, this is equal to d by dt of 2t square, and this is equal to d by dt of your 5. Okay, so just making you understand the basic rules again. So we know that d by dt of t to the power n is nothing but equal to n into t to the power n minus 1. Similarly, d by dt of a constant is nothing but equal to 0. So let us use these two rules and then find out the results. So therefore, for this example here, Vx is nothing but equal to d by dt of 3t, correct? Which can be said as 3 is a constant, we can put it out. Please remember, if only constant is involved, then it's 0. But if a constant is being multiplied by a factor or a variable which is same as that of denominator, then we can put the constant outside and just follow the derivative or the differentiation for the constant or the variable which is involved. Okay, so this can be said as 3 multiplied by d by dt of t. So what will be d by dt of t? So n factor is 1 here. So hence you can write this as equal to 3 into t to the power 0 by into 1. Okay, so then we will get it is equal to 3. Fine. Similarly, Vy is equal to d by dt of 2t square, which is equal to 2 into d by dt of t square, which is equal to 2 into t to the power 2 minus 1, which is equal to 4t. Okay, so we got Vx as 3, we got Vy as 4t, and because this is a constant, Vz would be equal to 0. So I hope you got that how we got dv of t is equal to dr by dt, and we differentiated it how we got 3i plus 4tj. Okay, so let me just rub and then start again. So therefore v of t is nothing but equal to dr by dt, which is equal to d by dt into 3ti cap plus 2t square j cap plus 5k cap, which was given in the question. Then we just differentiated it with respect to t, and therefore we got it is this as equal to 3i cap plus 4t j cap. Okay, now going with the similar, so this was the first part of the first question, that is velocity at any time t is nothing but equal to 3i cap plus 4t j cap. Okay, now let us do the similar result for acceleration also. We know what is acceleration. Acceleration is nothing but equal to dv by dt. Correct, is dv by dt. How we will put forward with this location here, this expression here, it will be d by dt into 3i cap plus 4 tj cap. Correct, so this will be equal to d by dt into 3 plus j cap into 4 into d by dt of t. Okay, so using the same result which you understood before, so for a constant this will be equal to 0, and for dt by dt it will be 1, therefore this will be equal to 4j, and that is the expression which we got for the value of acceleration at time t. Okay, so that is the thing which we got. So finally what we can say, that what is the as you can see clearly that the acceleration is always constant, which is equal to 4 in that along the y direction. Please remember, as it is only j cap, so therefore acceleration is always constant, but it is along the y direction. Okay, so that was the first part of this question. So finally, what is the answer of the first part? The first part says that the velocity is nothing but equal to 3i cap plus 4tj cap, and acceleration is nothing but equal to plus 4j. Okay, therefore acceleration is equal to 4 meter per second square along the y direction. Now let us look at the second part of this question. The second part of this question says that you need to find the magnitude and the direction of v of t at t is equal to 1 second. Okay, so first of all, what is the magnitude of anything? The magnitude is nothing but equal to, for a 2D plane, it is equal to vx squared plus vy squared. Correct? So therefore, what will be the velocity magnitude? It will be nothing but equal to 3 squared plus 4t squared. Correct? But as you can see clearly, it is being asked at t is equal to 1 second. So we can put the value of t equal to 1 here. So therefore, velocity at 1 would be nothing but equal to 3 squared plus 4 into 1 squared. We know this is a Pythagorean triplet, and therefore we got the velocity as nothing but equal to 4 meter per second. Sorry, 5 meter per second. Okay, that is the only thing which is being obtained. So therefore, at t is equal to 1 second, we got velocity is equal to 3i cap plus 3. This would be not 3. This will be 4. Okay, 4.2 j cap and so therefore its magnitude is v is equal to under root of 3 square plus 4 square, which is equal to 5 meters per second. As direction of v of t is also being asked at t is equal to 1 second, how to calculate direction? We know tan theta is nothing but equal to vy by vx. You know the value of vy at t is equal to 1, which is equal to 4. Value of vx is 3. Okay, that's how we obtained these values here, correct? So therefore theta obtained is nothing but equal to tan inverse 4 by 3. Okay, so this tan inverse 4 by 3 is approximately equal to 53 degrees. Okay, so that is how we can obtain. So direction is along the x-axis. Okay, so let us suppose I make a graph for this also. So let us say this is your velocity v. If you drop the perpendiculars from here, you will get this is equal to vx, this is equal to vy, correct? So if I make an angle theta here, so this angle tan theta is nothing but equal to vy by vx, and therefore we said in the last slide it is 53 degree with the x-axis. As you can see, this is your x-axis and this is your y-axis. So that is why we said that the theta is approximately 53 degrees with the x-axis. Okay, so you can remember this also, because these values will be will come very handy in the future classes. So tan inverse 4 by 3 is approximately 53 degrees, and similarly tan inverse 3 by 4 is approximately 37 degrees. Okay, so you can just keep remembering this so that it will be easy when these tan inverse or angles come in the subsequent classes in future. Okay, right, so that is the example for the motion in a plane. Now let us understand another topic, that is motion in a plane with constant acceleration. Okay, so let us try to understand this. What do we mean by constant acceleration here? The acceleration will be always constant. As you can see in the previous example also, the acceleration was constant. Okay, so please remember, if you remember correctly, in the chapter motion in a straight line, so just a quick revision so that we can understand the importance of constant acceleration. So in the chapter motion in a straight line, we derived basically 3 different kinematics equations. So just try to remember those kinematics equations, which was velocity at any time final is nothing but equal to velocity initial plus acceleration into time. And the second was a displacement obtained is nothing but equal to velocity initial into t plus half at square. And similarly, the third was that the final velocity when squared is equal to the initial velocity squared plus 2as. Okay, if you look at the acceleration value here and remember correctly, when these things were derived, we assumed it, or basically this complete derivation was only and only possible when we understood the acceleration as constant. Okay, so that's how we derived these expressions for the acceleration to be constant. Okay, so this is for constant acceleration. Let us understand now what this topic has to be understood, and then we can move forward. Okay, so let us understand a new subtopic, that is motion in a plane with constant acceleration. Okay, so suppose that an object is moving in the xy plane and its acceleration is constant. Okay, right, so we are supposing it. Over an interval of time, the average acceleration will be equal to this constant value. So it is quite evident. This will be also understood in the motion in a straight line also, that let's suppose there's an average acceleration happening. If the acceleration is constant, then the average acceleration is equal to this value. So average acceleration is equal to instantaneous acceleration for the case of constant acceleration. Right? Okay, let's move forward then. Suppose that an object is moving in xy plane and its acceleration is constant. Acceleration is constant. over an interval of time, the average acceleration will be equal to this constant rate. Now, let the velocity of the object be v naught at time t is equal to 0 and v at time t. Okay, so therefore, by definition, what we can write? We can write the average acceleration is nothing but equal to v naught is nothing but equal to delta v upon delta t. This will be equal to v final minus v initial upon t final minus t initial. We know that what is the velocity at time t? It is v. What is the velocity at time 0? It is v0. What is the time at final? It is t, and initial is 0. So therefore, from this we can say again that the vector v bar is nothing but equal to v naught vector plus a bar into t. Okay, so again we derive the same concept which was derived for your motion in a straight line also in the terms of vector notation. That is that was also in vector notation also. So it is again v bar is nothing but equal to v naught bar plus a bar into t. Okay. Now, as we know that the complete expression or complete vectors can be resolved into its components. So therefore, if we resolve it into components, we can get that the velocity vector at x. So as it is a simple addition here, we can directly add the vector components of these two and find the result. Okay. So therefore, what will be the velocity vector at time t in the x direction? This will be equal to v naught x plus ax into time. Similarly, what is vy? Vy will be equal to v naught y plus ay into time. Okay, so that was one of the expressions which we got. Okay, now let us find out how the position r changes with time. Please remember what is position r being talked about here. We can say that we need to find out how the position vector is being changed. Okay, so we follow the method used in the one-dimensional case. So let r naught and r be the position vectors of the particle at time 0 and time t, and let the velocities at this instance be v naught and v. Okay, so that is quite understood directly only. Now, then over this interval, the average velocity is v naught plus vy. Quite evident how this was how we looked up and understood the second kinematics equation derivation, third kinematics equation derivation also, that the average velocity is nothing but the mean of both of these velocities, which were v0, that is initial, plus final divided by 2. Okay. So then over this time interval, the average velocity is v naught plus v by 2. The displacement is the average velocity multiplied by the time interval. Okay, so this is quite evident. We know that what is displacement? Displacement is nothing but velocity into time. So what we can say that the average displacement or the complete displacement which is happening over the entire time interval range is nothing but velocity multiplied by time. So therefore, what is displacement here? Displacement is the average velocity multiplied by time interval. So therefore, what we did that displacement, that is r minus r naught, correct? Similar in the case in the case of your straight line, what we did delta x, that is equal to x2 minus x1. So here the displacement vector will be r minus r naught. Okay. So r minus r naught is nothing but equal to average velocity, that is v plus v naught by 2 into time. Now, what is average velocity? Average velocity is nothing but equal to v naught plus at. So, v plus v naught by 2 into t can be written as equal to v naught plus at plus v naught by 2 into time, which is equal to 2v naught by 2 plus at by 2 into t, which is equal to v naught t plus half at square. And that is how. So this is equal to r minus r naught. Therefore, r is equal to r naught plus v naught t plus half at square. And that is how we derive the second kinematical equation in the velocity form for 2D plane. That is nothing but r is equal to r naught plus v naught t plus half at square. Okay. So it can be easily verified that the derivative of above equation, that is dr by dt, gives v is equal to v naught plus at, and it also satisfies the condition that at t is equal to 0, r is equal to r naught. So what this line is explaining here, we know r is equal to r0. Okay, now let me explain this here. So what the second kinematical equation told us to about, r is equal to r0 plus v naught t plus half a t square. Okay. Now we know that velocity v is nothing but for instantaneous velocity is equal to dr by dt. Okay. Let us differentiate the above equation and try to find out the relation, that is v is equal to v naught plus at. Can we derive it or not? Okay. So how can we differentiate it? We'll write d by dt on both the sides. So it is d by dt of r, which is equal to d by dt of r0 plus v naught t plus half a t square. Okay. So this is equal to, we can separate all the terms in addition. So it is d by dt of r naught plus d by dt of v naught t plus d by dt of half a t square. Okay. So as we know that r naught is a constant, r naught is a constant value, so therefore this will be equal to 0, because it does not have constant, or basically it's a number which is not a function of t. So anything which is not a function of t will not change with t, correct? Because r naught is something which depends on space basically, or let us suppose it has a position x and y coordinates, correct? So it won't have any relation with t. If it doesn't have any relation to t, we can say that it is constant with respect to t, hence it will be 0. Plus, so here v naught is a constant, so we can just put it out into t by dt of t plus, here half is a constant. Please remember we are working with constant acceleration, therefore this will be here a into d by dt of t square, correct? Moving forward, this will be 0 plus v naught. If you remember correctly, dt by t, so I will write the formula again. So it is d by dt of t to the power n is nothing but equal to n into t to the power n minus 1. Okay, that thing being said, it is nothing but v naught into 1 plus half into a into, so what will be t square? It will be nothing but equal to 2 into t to the power 2 minus 1. So 2 getting cancelled. Therefore, we know what is dr by dt. Dr by dt is nothing but v at the instantaneous velocity, which is equal to v naught plus it. So hence this thing can be derived from here also. So basically, using this and differentiating it, finally we got to this relation, that is v is equal to v naught plus at. Okay. Fine. So that is the only line which is written here. That is, it is easily verified that the derivative of the above equation, that is dr by dt, gives v is equal to v naught plus at. Okay, and it is also satisfying the condition that at t is equal to 0, r is equal to r naught. Let's try to devise that also into scenario here. So it is written r is nothing but equal to r naught plus v naught t plus half a t square. Okay, so what happens at t is equal to 0? So r is nothing but equal to r naught plus v naught into 0 plus half into a into 0. It leads us to r is equal to r. That is how we can divide this relation. Okay, so we satisfied this condition also, that is at t is equal to 0, r is equal to r. Okay. Now, above equation can be written component form also. So as in the previous case, we wrote it in the component form. How we wrote it in the component form? As you can see here, vx is nothing but equal to v naught x plus axt, then vy is equal to v naught y plus ayt. In the similar case, we can write it here also. So therefore, what we can write? X is nothing but equal to x naught plus v naught x t plus half a x t square. Okay, Similarly, for y, it will be y is equal to y naught plus v naught y t plus half ay t square. Okay. Ax and ay would be constant here because we are looking at constant acceleration. Okay, but they will have some values which are different from a. Okay, may or may not, depending on whatever the scenario here may be. Okay, so they can be same also, but it is always constant. A is always constant. Okay, fine. So this thing is also explained how we can write this in the component form. So one immediate interpretation of above equation is that the motions in x and y direction can be treated independent with each other. So this is very, very important line because that is the basis or basic crux of understanding the projectile motion, which is the end of this chapter. Okay. So one immediate interpretation of the above equation is that the motions in x and y direction can be treated independently of each other. So there is no effect of these quantities on the below thing, and there is no effect of these below quantities on the above. Okay, so that is how we can say that the motions in a straight line or motions in a x and y direction can be treated independently of each other. Okay, fine. So that thing being said, that is the motion in a plane or two dimensions can be treated as two separate simultaneous one-dimensional motions with constant acceleration along two perpendicular directions. Okay, so again, that thing is only being written in a more easy language. That is that the motion in a plane can be understood as two separate simultaneous one-dimensional motions. So if we are able to resolve the vectors into two components, let us say in x and y directions, then we can directly apply all the concepts which we understood in motion in a straight line into motion in a plane. But please remember, there will be two different equations which are being worked upon depending upon the accelerations in those locations and basically the other terms such as velocities, displacements, etc. in those different axes. Right. So this is an important result and is useful in analyzing the motion of objects in two dimensions. A similar result holds for three dimensions also. So same thing can be worked upon in three dimension also. Just the choice of perpendicular direction is convenient in many physical situations. Okay, so the choice of perpendicular direction is convenient in many physical situations. So that is why, or that here we said as the reason, one of the reason, as in why we chose the unit vectors in our direction I cap, j cap, and k cap. Or basically why we are working with rectangular coordinate systems x, y, z, which are basically perpendicular to each. Okay, so that is for this only. Fine. So now let us try to understand the formula which we just derived again regarding the displacement. Okay, so let us understand from this question here. So a particle starts from the origin at t is equal to 0 with a velocity 5 I cap meter per second. What is the meaning of this? Let us suppose we are working only in x and y plane. So this was your x-axis, this was your y-axis. So basically we are saying that at t is equal to 0 with a velocity 5 I cap meter per second. Let us suppose they are starting from the origin. We are assuming they are starting from the origin. Okay, so what would have happened here? There would have been a velocity in this direction with a magnitude of 5 meter per second. Okay, it is written here, sorry. So we don't have to assume. It is written that the particle starts from origin. Okay, at t is equal to 0 with a velocity 5 I cap meter per second and moves in the xy plane under the action of a force which produces a constant acceleration of 3 I cap plus 2 j cap. So here acceleration is given to you to be constant, which is 3 I cap plus 2 j cap meter per second square. Okay. Now the first coordinate, the first question being asked is, what is the y coordinate of the particle at the instant its x coordinate is 84? Okay. Let us try to devise this. Let's not look at the B part right now. Let us first understand the A part and then we can move to the B part. Okay, fine. So let us first write each and everything which is written in the question and then we can move forward. Okay, so first of all, the V naught x is given to in the question as 5 meter per second. Okay, and v naught y is basically 0 meter per second. Okay, rest all what we need. Okay, first of all, let us write the equation here. So we know r is nothing but equal to r naught plus v naught t plus half at square. Correct? So therefore, what we can write, let us try to write the equations for your x and y because we can resolve it into two components. So therefore, what we can write, we know r naught is 0. The position vector at the origin or at the initial position is 0. So we know r naught is nothing but equal to 0 I cap plus 0 j cap. Correct? Because the particle starts from origin. So this will be 0 plus, what is the initial velocity? Initial velocity is 5 I cap plus 0 j multiplied by t plus half into, what is the acceleration value given to you in the question? It is 3 I cap plus 2 j cap into t square. Okay. Now just do some mathematical formulations and then we will get r is nothing but equal to I cap into 5t plus 3 by 2 t square plus j cap into this will be equal to 2 by 2 t square. Okay, so that is the final displacement vector you obtained. Okay, using this equation, what we can say? We can say that the displacement in the x direction, that is the x component of the vector, is nothing but equal to 5t plus 1.5 t square, and similarly the displacement vector in y direction is nothing but t square. Okay, so if you see this clearly, this is nothing but whatever thing which we have obtained till time t. So this is the thing which you obtained at the displacement vector at time t. Okay, now let's move forward. So now if we move forward, what we know that x coordinate is 84 meter. Okay, it is given in the question, so we can write that we just need to calculate now the time at which we got that coordinate to be 84 meter. So it is 84 is nothing but equal to 5t plus 1.5 t square. Okay, so this is a simple quadratic equation which is being formed, that is 1.5 t square plus 5t minus 84 equal to 0. So if you will do normal quadratic formula, it is minus b plus minus b square under minus b plus 1 under root b square minus 4ac upon 2a. We will finally get the answer is equal to 6 seconds. Just put this 6 seconds into this, and therefore you will get that y at 6 is basically 1.0 into 6 square, which is equal to 36 meters. So what was the question being asked? The question was asked, what is the y coordinate of the particle at the instant the x coordinate is 80? So I think we have completed with the first part of this question. Okay. About the second part, what is the speed of the particle at this time? So to find the speed, what we will do? We know velocity nothing but equal to dr by dt. Correct? So just finding out dr by dt, we can say that velocity is nothing but equal to d r by dt. Okay, in the previous example we have just calculated the value of r here. So if we just derive it, it is nothing but d by dt of I cap into 5t plus 1.5 t square plus j cap into 1.0 t square, which will directly lead us to 5 plus 3t I cap plus 2t j cap. So I just used two different formulas. One was d by dt of t is equal to 1 and another was d by dt of t square is equal to 2t. Okay, so that was the velocity being obtained, which is 5 plus 3t I cap plus 2t j cap. I will try to derive it again in the next part of the next lecture only. And therefore the speed at this time, so we'll just put the value of 6 here, and you will get 5 plus 3 into 6, which is 18. 18 plus 5 gives you 23 I cap, and similarly 2 into 6 is 12, so you get 12 GB. Okay. So what is the speed here? So speed is basically, we know that speed is nothing but the magnitude. So this is nothing but equal to under root of 23 square plus 12, which will give you the approximate answer as 26 meter per second. So and that is the final answer. So we obtained the y coordinate also when the x coordinate was 84 meters, and we calculate the speed also. Okay. So that is the end of this example. Okay, so let me stop the discussion here. In the next class, we will start with the relative velocity in 2 dimensions, and we will understand how it is different from the relative velocity in 1 dimension. So the course progress for you, we started with the introduction, then we went to scalars and vectors, then we understood the multiplication of vectors by real numbers, then the addition and subtraction of vectors, then the resolution of vectors, then the vector addition, that is analytical method, then motion in a plane. Then motion in a plane with constant acceleration is completed. And in the next class, we'll start with relative velocity in 2 dimension. It's a very small concept only. And then we can finally move to projectile motion and uniform circular motion. Okay. So that's it for this lecture. So thank you so much. We'll meet in the next lecture.